Okay, everyone. Today we're gonna talk about the conversion from decimal floating number into 32-bit floating point number, which has the IEEE 754 format. And this is the format that will be stored in memory, as we shall see. Okay, let's begin. Before we start, we will talk about two major things. We will see them in part one and part two. In here, in programming languages, when we write code like the variable declaration and assignment as shown here, now this X is memory location, it's an address. In this address, it will store this floating number that has the format of a float. As you see now, we will examine exactly how we're going to store this number in binary form. Now, this binary form has a special format called IEEE 754 format. Okay, we will check these in detail. This is going to be part one, which has the title Decimal to IEEE 754 Floating Point Representation. The second part will be the opposite. When in C++ or in Java, when we say print or print line, when we see C out of 1 and C out of 2, and we assuming that f1 and f2 are both were declared before as a float number and stored in memory, now when we read them, we have to convert this binary form into its decimal form. And this is going to be part two, which has the title IEEE 754 Floating Point Representation to its Decimal Form. Okay, let's start with the part one, but before that, let's examine and check together what do we mean by IEEE 754 format. Before we start, we have to check the term which is called scientific form. Scientific form is an important term in this topic, and let's study it. It's very simple, it's straightforward. Let's assume we have this decimal float number, which is 256.78, and we can write it in scientific form as like this. Now, this number and this number are the same, they are equal. But what exactly we did? What we did here is that we moved this point right two places. As you can see, this point come here and then come here, then we stopped here. It have to be next one digit. And we moved two places, that's why we put 2 here. That's why we put 2 here. So that's why now this number and this number are the same. It's very true. In this form, this is called scientific form. This is not scientific form. Let's check this number, 0.003678. We can write it down as, we can move now, we will move, now since we do not have ones here or non-zero, let's assume we have to move left by moving 1, 2, and 3, because this dot has to be next to one digit, non-zero digit. And as you can see, now we moved how many places? 1, 2, and 3. So that's why we make 3. But in this case, we have to make it negative because we move this point to the left. But when we move it to the right, we increment positive. So we increment the power if we move the point to the right. If we move the point to the left, then we decrement the weight or the power of our base, which is 10 in this case. This is the same thing. If it's negative, we have to move this point again 2 places to the right. That's why we increment the power of 10, and we keep the sign as the same. Now these are, as you can see, they are called scientific form. Okay, let's examine the scientific form as a floating point decimal number. As you can see in here, this is minus. In this case, it's called the sign of mantissa, and this is the decimal point, and this is the mantissa, and this is the base. This is the sign of the exponent, and this is the exponent. Again, we're going to have the similar thing when we in the process of conversion. That's why we check on this. It's very straightforward. It's very simple. Okay. Now let's see what are these IEEE 754 format. We have two forms, which called single precision. The second form is double precision. In single precision, it's 32-bit. In 32-bit, we have 3 parts. First part called sign bit, second part called exponent, and mantissa. Now the sign bit is 1 bit, the exponent 8 bits, and the mantissa is 23 bits. Total we have 32 bits. The same thing, similar thing in double precision when it's 64-bit, one sign again, 1 bit for the sign, 11 bits for the exponent, and 52 bits for mantissa. Now this part is much more accurate than this one. Anyway, now we will focus in this 32 bits, which is the single precision. As you can see now, this is the form of IEEE 754 that has the 3 parts. Now this part called mantissa, which will be represented using 23 bits, and this part called exponent, which we assigned 8 bits for it, and the last part is 1 bit will be the sign of the mantissa. Okay, let's start by taking example. This will clarify all the details. Now, in this example, we declared x as a float. This is the variable data type, and we assigned the number 263.3 in this memory location or memory address as x. Now the question now is how x is really stored in RAM, how this number is really stored in RAM. Of course it will be stored in IEEE 754 format, but let's see how we make the conversion. Okay, first step is, now this number has 2 parts. You see the point here, the decimal point, it has its right and it has its left. Now we will take this part, which is 263, and we convert it to binary. This is straightforward to process. By long division, it's very straightforward to process. We don't want to go through into this and assume you already know how to convert from integer to binary. Okay, now this is the first step. The second step is to convert this 0.3. As you can see, 0.3. This is the number. This is the number of after the point. And when we convert it to binary, and now this is going to be the result. Now we will see how this is done. We do this by multiplication. Now we start with 0.3 and we multiply by 2. Why 2? Because 2 is the base number that we will convert to, which is in binary in this case. It will be 0.6. Now the number before the point is 0, we put it here, plus 0.6. Now these two equal this one. Now we take this one, 0.6 times 2 is going to be 1.2. So we take 1, which is the before the point, and we added 0.2. Now we will take this 0.2 times 2, it's going to be 0.4. As you can see, what's the point? What's the before the point? It's 0. Now we will take care of this. Now we need these numbers, so we read the number from top to the bottom. Okay, as you can see, as mentioned here. Now this we will put 0 point, and then this is the first 0, then 100, which is 100, and then 1100, 1100, and then 1100, 110. And as you can see here, we have a pattern. In fact, that's why we can stop anytime. It depends on the accuracy we need. We will see that how many bits we need in this case. Okay, now, so this part we already converted to binary, and this is the part. This is the decimal part, this part that we converted to binary. Now we combine them. As you can see, now this is written in blue, this is in red. This is the direct binary representation of this floating number. But this is not how it's stored in memory. We are not done yet. Okay, let's move forward now. We have to convert this to scientific form. We already checked together what do we mean by scientific form. In this case, as you know, this number times 2 to the power 0. Now, if you want to convert it to scientific form, you have to move this point. How many places? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. And we stop here. So that's why we, as you can see, this is the point moved here. And now we incremented the power to the 8. Now this is why it's 8, because we moved 8 places to reach this first one. Okay, now this is called scientific notation. This is the scientific form we look at. Now, when we reach this step, first of all, we will take this 8 and this 8 generated according to the shifting amount we move to the right in this case. If we shift left, which we'll see in another example, this is going to be negative. Okay, now this 8 we will add it to 127 because we are talking about 32-bit floating point number, and the result will be 135, which we have to convert it to binary. In this case, it's going to be 1, 4 zeros, and then 111. As you can see, these are 8 bits. Okay, this is the first step. The second step, we will take now this. From this point, we will count 1, 2, 3, 4. We will count 23 bit, and we will put them. This is going to be our final mantissa, and we will put this number. See, this is our exponent, and this is our sign. Our sign we can check from this one. In this case, this is positive. That means we will put it as 0. So this is how it will be stored in memory. But as you can see, check, this is the mantissa, which is 23-bit. This is the exponent 8-bit, and this is the sign of mantissa, which is 0. But let's not forget something which is important, which is rounding. We will check this bit. Now this bit is not included in the mantissa. It's right after the mantissa. I mean, you count here 23. This bit will be 24th bit. We will check if this bit is 0, that means there is no rounding. If it's 1, that means we will round, and by rounding we mean we adding 1 to this mantissa. Now this is important. We will see example to clarify this step. In this case, since this is 0, that means there is no rounding, and this is our final result. As you can see, now this is the decimal form, this is the binary form which will be stored in memory, and this is hexadecimal form. And in RAM it will be stored like this. See this one, 0100, as you can see, 0100, 0011, 00, and next byte, since it's 4 bytes, it's 32-bit, means 4 bytes. This is how it's gonna be stored in RAM. Okay, we're proceeding with example 2. In this case, we are checking, we make the variable declaration and assignment, floating y equal minus 0.005. So we will check together and see exactly how this number will be stored in the memory address y in the float format, which is IEEE 754 format. Okay. Now in this case, we will take the same process as we did in example 1. This point, there is nothing in here, it's 0, so it's the same, it's easy. Now this part we will convert it to binary form, direct binary form, which has the base 2, and in this case, okay, yeah, 0.005, this is 10. When we convert it, this is the final result. Let's see how this has happened. I have some mistypo here because 2 has to be here. This is the base. Okay, anyway, so let's start how this is done. 0.005 times 2 equals 0.01. We will take this, the after point, which is 0, we put it here, and we add 0.01. Total will be this one. Now, 0.01 times 2, this one, 0.01, it's here, times 2 equal 0.02. After the point is 0, we put it right here, plus 0.02. Now, 0.02 times 2 gonna be 0.04, which is gonna be 0 plus 0.04. Now, 0.04 times 2 gonna be 0.08, so it's gonna be 0 plus 0.08, etc. Let's get here. 0.64 times 2 gonna be 1.28. So that's why we put the 1 here, and when plus 0.28, etc. Now we will read the number from top to the bottom, which in this case gonna be 1, 2, 3, 4, 5, 6, 7 zeros. As you can see 0 point, and you put here 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. Then 101, 101, and then 3 zeros, and then 111, 111, etc. Okay, you can proceed with this one because I have limited space here, so you can continue as much as you like. Okay, now so the whole number, which is this one, will be like this. Now we will convert this one as scientific form by shifting left in this case. Okay, let's check what's going on here. Now this number times 2 to the 0. This is the initial step. Now we have to convert it to scientific form by moving this point left. How many places? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. I stop here because now I have the point and I have the leading one. Okay, so that's why we put minus 8. If we if you remember in example 1, we moved 80 places to the right, so that's why we put it 8, not negative 8. In this case, we move left 80 places, that's why we put minus 8. Now, so the final, after being the scientific form, gonna be like this. This is 1, this is the 1, the same as you can see, this one, and then we put the point, then 0, 1, 0, 0, 0, as you can see, 0, 1, 0, 0, etc. Same number. Now we will use this number, which is minus 8, and we will add it with the 127, and the result will be 119, and we convert 119 into binary form. As you can see, it's going to be 1110111. Okay, now first of all, let's set up our final result by putting this mantissa. Now how many bits should we count? 23 bits. These 23 bits, we will put them right here, as you can see. And for this one, we will put the exponent, the final result. But notice here that this 1110111 are 7 bits. As you can see, that's why, but we need 8 bit because the exponent is 8 bits. So we put here 0. Okay. Now this sign here will be 1. Why it's 1? Because this is negative number. It's straightforward. Now, is there rounding? Okay, we will check in this one, which is the bit 24, as you can see, and since it's 0, that means there is no rounding, and this is our final answer, which is written like this. Now this is the decimal form, binary form, and this is the hexadecimal, and it will be stored like this. Clear? It's clear. Okay. Now let's move forward to example 3. Okay. In this example, it's the same steps we saw in example 1 and 2. In here, we will store this number in the memory location Y, and since it's a float, that means we will store it in IEEE 754 format. Okay. First step, we have to convert the 35. So let's ignore now the minus. For now, we're just gonna convert the 35 into its binary representation. This is direct conversion by a long division. Okay, and we come to this one, this part, which is 0.25634, and we have to convert it into binary, and this took some time with me, but let's check it out. Now 0.25634 we have to multiply by 2, and this is the result. The result has 2 parts. This is the 0, and then this is this part. Now this one we multiply by 2, the result will be 0.02536, and it's gonna be equal 1 plus 0.0. I hope this is clear. Now you keep moving until you reach enough. You have to do the number of digits enough to cover this 23-bit for our exponent. Okay. Now the whole number will be combined, this one and this one, and now we have to make it the scientific notation. And in this case, since we do not have 0 here, then we have to move to shift right. How many bits should we shift? Let's see. Now we have to move this decimal point 1, this point 1, 2, 3, 4, and 5. We do not exceed this one, so we stop right here. Okay, now so we have to increment this one to become 5. It's clear now. It's in scientific notation. Now we get this number and we add it with what? With 127. The same steps. It's gonna be 132. 132 will be in binary form 1, then 0000100. It's 8 bits already. Okay. Now this is our mantissa. We will count how many bits? 23 bits from the point. You count 23 bits and we just put them here, as you see. and this is our exponent, the same, it's in 8-bit, and this is our sign, which is we can determine using this one. It's 1 because this is minus. Now we will check about the rounding. Is there rounding here? In this case, yes. We see this, the bit 24 is 1. 1's mean that we will round. By rounding, we mean we adding 1 to the mantissa. So when we add 1 to this one, this is going to be what? Instead of 0, 1, it's going to be 1, 0. So this is the updated final result. See, this is the sign, the exponent, the mantissa. Not this one. This has become wrong because now we made the rounding. After rounding, this is the final updated result. Now we take this result and this is going to be stored in RAM, as you can see. Okay, I hope these examples are clear, and we'll see you in part 2. Thank you very much. See you next time.